Okay, welcome back. So we looked at some examples of covariance functions or correlation functions, and of course it's also of interest to have a single measure that measures how well a random function remains dependent or correlated in space or time. And for that we have a number of so-called correlation parameters. Now, one is the so-called correlation length or effective range, and that is that lag at which the correlation becomes 0 or smaller than 0.05. This is called this then is called the actual range or correlation length or range of the correlation function, and this is called the effective range because an exponential one only goes to 0 at infinity. So we have to find some value, and this is actually this 0.005 is usually reached about 3 times the range parameter that is in the function, e to the power of minus h divided by L, by lambda. Then 3 times lambda is often the effective range. Now in time there are other measures. One is the so-called integral scale. That is the area underneath the correlation function. Yeah, you can imagine the longer it takes for the correlation function to go to 0, the larger the area underneath is. And in certain publications, one talks about the so-called scale of fluctuation. And the scale of fluctuation is actually is quite similar to this, but now it's 2 times the integral scale because because the correlation is an even function. You integrate it between minus infinity and plus infinity, and you get actually 2 times the integral scale. Now the integral scale can also be defined in 2 or 3 dimensions, and this is shown here. This is the integral scale in 2 dimensions. This is the integral scale in 2 dimensions and 3 dimensions. You see here that the value of pi appears, and that has to do with the fact that we're actually integrating in expanding circles like that, right? So this is where the pi comes from, or extending spheres in 3 dimensions. Yeah. So that is the 2 and 3D versions of the integral scale. So you will see sometimes if you read the literature that somebody might say that the logarithm of hydraulic conductivity is modeled by a wide-sense stationary random function with a multivariate probability, Gaussian probability density function with a mean of the log conductivity equal to 2 and a variance equal to 1 of the log conductivity of 1.5 and an integral scale of 2.5 kilometers, something like that. And then if they say that, this is what they mean by integral scale. Okay, now we're moving to a slightly totally on a different subject. That is the so-called conditional random function. Of course, like I said, we do have observations often. So if we have, for instance, in this case, this is a random function of time. It may be that we have 4 observations of. We may have 4 observations of the reality. So the actual random function of the actual realization of the random function that signifies reality at, in this case, 4 points in time. Now this enables us to look at a subset of all the possible realizations, namely the subset of realizations of the random function that pass through the observation points. And of course, because this is a subset of all possible realizations, it reduces the total uncertainty that we have about the uncertain variation in time. Yeah? So now we're only selecting those realizations of the random function that exactly pass through the observations. And this subset of realizations together make up the conditional random function. It's a random function whose realizations are conditional on the observations, in that they are exactly equal to the observed values, assuming that we don't have an observation error now, for now, at those points where these where this phenomenon was observed. And of course, what you see, these are 4 realizations of the random function, that obviously, if you are further away from an observation, then there is larger uncertainty, because there's larger uncertainty than when you are close to an observation. And this is the conditional probability density function of the random variable at T1 between 2 locations, and this is one very close to a location. And because each single realization is continuous in time, of course, if you're very close to an observation, because they all have to pass through that observation, there's little room for these different realizations to be very different. But if you are farther away from an observation, then the uncertainty is larger. So the uncertainty now is conditional upon the distance to the observation. Yeah. So you also see that a conditional random function is no longer stationary. Because the mean is the dotted line that passes through all the observations, is not constant in time, and also the variance is different depending on whether you're close to an observation or not. So even though an underlying random function may be stationary, in what form, whatever, if you start conditioning, if you start adding observations and then construct the conditional random function from the non-conditional one, the underlying one, then the resulting conditional random function is non-stationary. Now, just to go ahead, when you do Kriging, for instance, Kriging interpolation tries to estimate directly from the observations this dotted line here, which is the conditional mean. Yeah? And of course, in a simulation mode, we can simulate multiple realizations of the random function that are all equally likely. They have the same similar statistical properties, but they all pass through these points here. Yeah? Now, this is an example you can play around. You can start. You can condition or not. And also put in, so there's a conditioning point here at time 30, and you can play around with the value of the conditioning point, what the value is, and of course you can also change the ensemble size and do an unconditional simulation or a conditional simulation. Now, if you have a conditional realization, a conditional random function, sorry, then this is usually portrayed as Z at T, given that we know the value of Z at given that we have observations at n different locations. Then, of course, we also have a conditional density function, which is the probability density of Z at T1, given the observations that we have. And again, notice that this thing now changes depending on T, yeah, on time. This is no longer the same everywhere, because a conditional random function is not necessarily stationary. And because we have the conditional probability density, we can also calculate the conditional mean and the conditional variance. Now, any set of methods like forecasting in time series analysis, updating a state in Kalman filtering, or Kriging interpolation. I already said that these are special cases from applying Bayes' rule to, and Bayes' rule is actually one way of conditioning random functions. Yeah. So we apply the rule of Bayes to find the conditional function z given the observations, and all of these things like Kriging, Kalman filtering, time series analysis in forecasting mode, these are all special cases of constructing a conditional random function, either in space-time or space-time. Okay. Now let's move back to an old known of us, the Rhine discharges. What I've plotted here is the correlation function of the Rhine discharge. Now what you can see is there's something happening here. It's periodic, because what you see is that it goes to 0, say after 60 days, and then after 200 days, so it's quite a long correlation. But then it goes up again, and then it becomes even negative later on. How is that? We see these peaks at 365 days, 730 days, and so on. Of course, this is exactly a year, and this has to do with the periodicity of the signal, because most of the higher discharges in the Rhine occur during the winter time. So what you see is that you get higher correlations between a discharge in January and a discharge in January the next year than between the discharge in January and the discharge in August. So obviously a random function like this has periodicity in it, and to explore that periodicity, one can actually go to a different portrayal of the fluctuation of a random function, and that is called a spectrum or spectral representation. And the reason that it's a good idea to do so is that lots of the time series have a seasonal character. Now, what is a spectral decomposition of a series? This is done here. Here you see a realization of a random function, whatever, it can be discharge or groundwater table elevation or whatever. And what can be proved if this is a realization of a stationary random function, yeah? Then we can decompose, we can actually construct realizations of this random function by a sum of random periodic functions or cosine functions. So this z is, if it's a fully stationary random function, it has a constant mean, and then it's an infinite sum of different components, where we can see increasing frequencies. So omega is 1 divided by omega is actually equal to 1 over the wavelength, yeah. So the frequency increases, and there is a random phase shift. So this thing has a random phase shift, phi, and this is a uniform random variable between 0 and 2 pi, yeah, on the circle. So it's a random phase shift, and it has a random, each component has a random amplitude, and this amplitude is a Gaussian variable with a certain variance and a mean 0, yeah. So how does that work? So you can see here these random periodic functions with random amplitude and with a random phase shift, and if we add those up, if we choose the variance of the amplitudes correctly, we can reproduce exactly the statistical properties of the underlying random function of this particular realization. So a random function can be decomposed, a stationary random function can be decomposed into random harmonic functions. That's the conclusion here. Yeah. This looks a little bit like what some people know a spectrum or a Fourier decomposition of any function, but now it's a random Fourier decomposition because both the amplitude and the phase of each function is random. And in Fourier, these are usually the phase shift. These are exactly fitted on the function at hand. In this case, they are random. Now, if we decompose a stationary random function in its correct random harmonic functions, and this is done such that we reproduce exactly the mean and the covariance function and the variance of this, and or even of this specific stationary random function, then we can plot the variance of each of those. So this is a plot where we plot the wave number, which is the frequency. So the frequency increases from here to there. These are very low frequency, long wavelength signals, and these are very high frequency signals. And what we plot here is against the wave number, the variance of the amplitude of the harmonic with that particular wave number. And as you can see, this forms a certain function, and this function is called a spectrum. It's often denoted by G. Yeah. So the spectrum is actually nothing more than a plot of the variance of the amplitude of the harmonics against the wave number of each harmonic. Yeah. Now this, of course, has an analogy with a light beam, because you can imagine that you can decompose light into different frequencies, and the relative abundance of each frequency in the total light signal or electromagnetic signal is, of course, the spectral signature of that electromagnetic signal, right? And this is the same. The relative abundance is measured by the variance of the amplitude. This is how important that particular frequency is in the total signal. And so by plotting the variance against the wave number or frequency, we get a spectrum which is very analogous of a spectral representation of an electromagnetic signal. So this is an alternative way of characterizing the temporal or spatial structure of a random function when it's stationary. By the way, if we add up all the variances, yeah, so we add up all the variances like this, we actually get, all the variances of the harmonics, we get the variance of the total signal. We get the variance of the underlying random function. And if we then, this is for the discrete, this is for the spectrum at a number of discrete points, but if we have a continuous spectrum, so we take not a finite number of wave numbers, but we take basically all the possible frequencies that we can have on the continuous line, then we get a spectrum that's continuous. And then if we take the area underneath this spectral density function, we get exactly the variance. And what is the analogy? Well, it actually, the variance of Z, therefore, yeah, which is the sum of all the variances of the amplitudes of all the different contributing harmonics, the sum of that is the total energy that is available in the process. If you take it the analogy with a spectrum, if you take the area, if you integrate the area, or we estimate the area underneath the spectrum of an electromagnetic signal between 0 and infinity, so the total area underneath that spectrum, that is nothing more than the total energy in watts that is in that electromagnetic signal. And similarly, this is the energy or a measure of the total magnitude of the random function, the variance of z. Now, this is an alternative way of representing the variance, the variability, and also the spatial or temporal structure of a random function. Now, the other way to represent the variability and spatial structure of a random function, a stationary random function, remember, was the covariance function. And the two are therefore related, the spectrum and the covariance function. And they are related by these particular two relationships, which are called the Wiener-Khinchin relations. So if we know the covariance of a stationary random function, we can use it to, we take the so-called Fourier cosine transformation and get the spectrum. The other way around, if we have the spectrum and we take the Fourier the Fourier transformation, we get the covariance function. Yeah, so they are related. Now, so they are couples. You have a covariance function, have a spectrum. So if we take, for instance, this is a time random function with a really shown here a realization of that has an exponential covariance function, then this is what the spectrum looks like. If you have a deterministic signal that is a exact harmonic, obviously the covariance function has this periodicity, and as you can see, this only has one wavelength, so the spectrum is a so-called Dirac function, so it's 0 everywhere and infinity exactly at the wavelength of the deterministic signal. Yeah. If this is a so-called Hall type random function, it has a exponential type of correlation function, but it goes through 0 and then it basically phases out to 0 at larger lags, and this is the spectrum of that. And then we have the white noise one, and you can see the white noise has a Dirac pulse, also has a correlation of 1 at, this is the covariance function, so the correlation is 1 at lag 1, and the variance is actually infinite, and the correlation and the covariance as well is 0 everywhere, and the spectrum is a horizontal line. Now, what is interesting to see is that obviously if we take the total energy that is in white noise, which is the area underneath the spectrum, you can see if we integrate this one between 0 and infinity, we get that the variance is infinite. And that's true, the variance of a continuous white noise process is infinite. And that also means that the total energy that you need to generate a process like that is infinite as well. So in reality, an actual white noise process cannot exist, because we don't have all the energy available in the universe to generate it. However, as a mathematical construct, it can exist, and it's often used to approximate so-called wide band noise processes. A wide band means that the spectrum is, the spectral density has quite large values over a wide spectral band. So the spectrum goes to 0, like I show here, but it goes to 0 very slowly. And these wideband noise processes are often approximated by a white noise process. Now, what is a spectrum good for? Because we already have the covariance function. Why use a spectrum? Well, of course, you can analyze periodicity in data and then can use the most dominant signal. If you take it out, yeah, if you decompose a signal into its random harmonics, and we have one of those harmonics that is very prominent, maybe the yearly periodicity, you can take it out and then you have and add up the remaining stochastic harmonics, and you end up actually with a stationary random process where the periodicity is filtered out. Yeah, that's one way. You can also leave out other wavelengths. For instance, if you're very interested if you may be even more interested in the very long wave or low frequency signals. Maybe you want to detect whether there is a El Nino effect in the discharge. So you don't, if you want, and these are long wave modes in the climate system. So if you want to detect those, you may want to filter out the smaller wavelengths, so the high frequency, so the high wave numbers. That's another reason to apply a spectral representation. And finally, as we will see later in chapter 8, if you have a differential equation, for instance, of the groundwater flow, where hydraulic conductivity is a random function of space, you can use a spectral representation of the random function of hydraulic conductivity to arrive at solving a stochastic differential equation. So you get the mean and the covariance of the hydraulic head, for instance, as a function of space and time. And to do that, to solve that analytically, often one reverts to a spectral representation of the underlying random function of hydraulic conductivity. And that's also in the syllabus, and we will see that later. Then finally, there is this is the spectrum of the Rhine data set. And obviously, you can see that there's a spike at once every 365 days, obviously. So, and there's actually also a spike at a frequency of once every 4 to 5 years. So if anybody knows what that is, I suspect it has to do with the North Atlantic Oscillation, maybe, or these large-scale phenomena like that. But because this is a significant spike here, but what it is, we don't know. Okay, with that, I'll end this part of the lecture.